Hello everyone, my name is Katerina and this is our final project. Here we simulated tea steeping in water, modeling how tea spreads through a cup and how temperature changes that process. When you drop a tea bag into water, two things happen: diffusion outward and sinking, since tea is denser than water. Together they create a circulation loop, and both of these effects get stronger in hotter, less viscous water. Our goal is therefore to model all of this computationally. In terms of how the simulation actually works, the mug of water is represented as a 100 by 100 grid of cells, where each cell holds a value from 0 to 1 from pure water to full tea. At every time step, tea diffuses into neighboring cells, and denser cells drive a downward flow. The water temperature instead controls how fast both of these processes happen.
So this white strip here at the top is the actual tea bag. And as the simulation runs, you can see that the tea concentration is spreading downwards and then outwards along the bottom of the mug. And this isn't just diffusion. This is actually due to buoyancy as well, because as the tea solutes dissolve, it increases the density of the water, and then this heavier water falls down to the bottom of the cup, and which forces the pure water, which is lighter, um, to get pushed up and out of the way. And this creates circulation loops shown here on the screen. Um, but this process is actually really slow, and the speed at which it runs is mostly due to these convection currents and not to actual diffusion. If we rely just on diffusion, it would actually take days, which proves that this physical mixing and fluid flow from the difference in density is what actually drives the tea mixing process. We also added some temperature sliders to see the effect of temperature on the system. You would think that heating the water would make everything happen faster because molecules are vibrating faster, which makes diffusion speed up, which is true, but we saw something a bit more complex. For cold water, which we said was 20 degrees Celsius, the water is actually really thick and viscous, and the high viscosity resists the buoyancy of the tea. The fluid can't easily flow, which means that the tea um, spreads slowly and evenly, mostly through diffusion, and we get very little circulation. Once we heat the water to 60 degrees, the actual structure of the water changes because the heat breaks down hydrogen bonds between water molecules, which means that the kinematic viscosity of the water drops by a lot. And this means that the heavy tea can now push the water out of the way, and we do start seeing those downward convection plumes forming. And in this regime, we see that diffusion and circulation are both contributing to the mixing of the tea. And once we heat up the water to almost boiling, the viscosity of the water is really, really low, and there's almost no resistance to the flow of the tea. And in this regime, we mostly see fluid dynamics take over. The heavy tea falls down very quickly, and we see like strong circulation loops that help the tea mix inside the mug very quickly. And in this regime, we do see that those convection currents are the primary reason why the tea is mixed. And we see that going from cold to hot water doesn't just make diffusion go faster, it changes the physics so that we go from a regime where diffusion is the main cause for mixing to a regime where convection is the main cause for mixing. So our code is split into two parts. We have the simulate.py file that runs the simulation, reads settings, and saves the output. And we also have a config.json file that has these settings and parameters like temperature, diffusion coefficient, and buoyancy parameters. Once the simulation finishes, the simulate.py file generates a GIF so we can see the actual simulation. And it also generates a raw JSON data file that plugs into an interactive browser tool with sliders so we can tweak any parameter and see how it changes the simulation. Obviously all of this requires a lot of operations for each frame. So instead of using standard Python loops, we use NumPy. So we could use fast vectorized array math to keep the simulation optimized and efficient. To calculate fluid behavior, we use forward Euler time integration scheme to solve fixed second law for the diffusion transport. And to make the simulation respond to heat and temperature, we couldn't use one singular diffusion coefficient. So instead, we implemented the Stokes-Einstein equation to calculate the relationship between the temperature and the water's viscosity and diffusion coefficient, so that we can make sure that once we change the temperature, it actually changes the way that the code works.
Moving on now to concepts learned, starting off with physics. We learned that diffusion and convection are two distinct mechanisms as far as like teabag diffusion are concerned. Temperature is going to control the balance between diffusion and convection. Small density differences can drive surprisingly strong flows, and that's true for many fluids, not just water. Numerical methods, as far as like actually simulating is concerned, solving fluid flow without having to track pressure is possible in 2D. It is one of the assumptions that we made, that the fluid is incompressible, which leads to a lot simpler math. Time steps have to be small enough for the simulation, otherwise it blows up. And obviously utilizing the tools that we have from NumPy is going to make the algebra a lot easier, and for the code to move a lot faster. From the project as a whole, building complexity in stages makes debugging much easier. We used a GitHub flow that allowed us to have branches for each additional piece that we wanted to add on. Visualizing the output at every step is essential. It helped us understand what parts of our model were and were not helpful in making it as realistic as possible while keeping the complexity down. And on that note, simple models can capture surprisingly realistic behavior. Finally, in conclusion, we had a simulation that produced relatively realistic T-steeping behavior. We noted that temperature changes how the T mixes, not just how fast. The bag size and shape will also obviously affect the strength of the circulation. The interactive tool makes it very easy to explore any scenario, and you can qualitatively check your work using an actual cup of tea and just watch as real life plays out as the simulation did. Potential next steps are letting the tea bag run out over time, so not having it stay at a constant concentration within the bag, but allowing it to lose concentration. Adding a temperature gradient across the mug, so taking our boundary conditions and relaxing them a little bit, allowing power to flow in and out of the mug, and then finally extending into 3D, which is going to require a lot more computation, but we were very satisfied with what we had so far. And finally, thank you for listening. We'll open the floor for questions now. Thank you.